Okay, moving on to our next functional group, we're going to discuss ethers in this video. And so an ether is when you have a carbon and then an oxygen and then some other carbon-based group like this. So it's an oxygen stuck between two carbons. That would be an ether. And so as I just stated, an ether is a compound that has this functional group where we have a carbon, and then an oxygen, then a carbon. Common names for ethers are obtained by naming the two groups attached to the oxygen and then adding the word ether. And so if you take a look at some of the examples here, you can see that also when you identify the groups, if you have two different groups, you have to list them in alphabetical order. So of course, ethyl would come before methyl, methyl would come before propyl, et cetera, et cetera. And then it says if the groups are the same, it's appropriate to use the prefix di, as in diethyl ether. So sometimes the di is omitted. So let's take a look at the examples here. So you can see on the first one, we've got a methyl group here, right? We should know a methyl group, and we have an ethyl group here. And so we'd call that ethyl methyl ether. So ethyl methyl ether. You see on the one below it, we have two methyl groups. So you could call it dimethyl ether. That's what I would call it. But some people just say methyl ether. They like you said, they leave out the di. Either one is totally acceptable. Next one, we have a phenyl. So we have a phenyl here, and then we have an isopropyl group here. So I'll just use this color. So we have an isopropyl group here. So note that I comes before P. So we have isopropyl phenyl ether. And then an ether that's pretty famous is down here, and that is diethyl ether. So you have an ethyl group here. We have another ethyl group here, and that is diethyl ether or ethyl ether. And one of the reasons why diethyl ether is famous is because it was used as an anesthetic. It's not a very good one. It's highly flammable, and it causes severe vomiting if it's used as an anesthetic, but it was used as an anesthetic at one point before better ethers were developed that are usually ethers that have fluorines on them, which renders them non-flammable, and they're a lot better. Example 9.8, assign a common name to each of the following ethers. So on this first one, we've got a methyl group. So that is a methyl group. And then here we have a phenyl. So this you guys recognize as a phenyl group. Well, M comes before P, so this would be methyl phenyl ether. So we'll put here methyl phenyl ether. And this one, you see that both of the groups are identical. We have a propyl group here, and we have another propyl group here. And so we would call this dipropyl ether. Or you could shorten it to just propyl ether. Propyl ether. So let's say I gave you something like, oh, I don't know, something like this, where you have something like this, and there you go. So what would this compound be? Well, you can see that these are both isopropyl groups. This is an isopropyl group, and this is an isopropyl group. And so this would be diisopropyl ether. All right. And so again, if we have two different groups, we list them in alphabetical order. And if we have two groups that are the same, we can put di in front of it, or you can omit the di. I didn't do it for the isopropyl ether. But there you go. That's how you name an ether. And just keep in mind, if I ask you a question on an exam about this, I'll give you an alkyl group like methyl, ethyl, propyl, isopropyl, or one of the four butyl groups, tert, butyl, isobutyl, sucbutyl, and isobutyl, so that it's something that you can always something that you can name. Now, properties of ethers, first of all, it mentions a heterocyclic ring, which is a ring containing at least one atom of an element other than carbon. And so you see a couple of examples here of heterocycles. We have furan and pyran. So there's furan and pyran. And keep in mind that all these atoms in the ring are carbons, and they, of course, have hydrogens attached to them, right? So there's furan and pyran. So again, a ring that contains at least one atom that's not a carbon is considered a heterocyclic ring. Um, I can name a bunch of others, but there's one that looks like this with a nitrogen stuck in it, like this. This is called piperidine. Piperidine. Okay. There you go. So there are many, many examples of heterocycles out there. But just to turn our attention to intermolecular forces for a second, it says here that ethers can hydrogen bond with water, but they can't hydrogen bond with themselves. So if you have a mixture, let's say you have an ether in water, and the ether that they're showing here is dimethyl ether. Well, you know that on the oxygen, we have our delta negative, right? Because oxygen is more electronegative than either of these carbons. And so we can see a hydrogen bond between the oxygen of the ether and the hydrogen of water. And there's our hydrogen bond right here. However, if you have a pure sample of two ethers, there's no hydrogen bonding between them because the oxygen, sure, there's an oxygen in each one of these. However, neither of these oxygens are attached to a hydrogen. And you remember for hydrogen bonding, we have to have a hydrogen that is either bound to an oxygen, to a nitrogen, or to a fluorine. So again, both of these compounds contain oxygens and hydrogens, but none of them are bound to each other. Whereas if we look at the example that's shown over here, of course, in water, we have a hydrogen bound to an oxygen. We have it occurring twice. And so the hydrogen from, again, the hydrogen from the water can do a hydrogen bond with the oxygen from the ether. Okay, so now we're going to move on to amines. And a couple things I want you to know. One of them is that amines are bases, okay? They're organic bases. So we'll just put here, they are weak bases. Okay, amines are weak bases. We talk a lot about acids and bases in chemistry class, and so I want you to know that an amine is a weak base. It's not a strong base that would burn your skin like sodium hydroxide or something, but amines are basic. And if something is a base, that means it's going to be a proton acceptor or a hydrogen acceptor. All right, so what is an amine? Well, if you've ever smelled stinky fish smell before, that you were smelling an amine. If you've ever experienced rotten fish odor. So an organic compound derived by replacing one or more of the hydrogen atoms of ammonia with an alkyl or an aromatic group, as you see here. So the first compound that they shown here, okay, this is NH3. This is ammonia. But now what they've done is they've replaced this hydrogen with some kind of R group. Now that would be some kind of alkyl, like it says alkyl or aromatic group. And so when we have only one R group on our nitrogen, we call this a primary amine. You can see where I'm going with this. If you have two R groups, right, one, two, we call that a secondary amine. And on the last one, we have three R groups, so we call this a tertiary amine. So primary, secondary, and tertiary amine. And of course, you can abbreviate them with their condensed structure. So this would be a primary amine, a secondary amine, or a tertiary amine. So this one is primary, this one is secondary, this one is tertiary. The common names are used extensively for amines with low molecular weights. These are named by alphabetically listing the names of the alkyl or aromatic groups bonded to the nitrogen and then putting on the suffix amine. The name is written as one word, and the prefixes di and tri are used when identical alkyl groups are present. So if we look at the first example on the bottom left, you have a methyl group, so that would be methylamine. If you have two methyl groups, well, then it's dimethylamine. And on the last one, we have a methyl group and we have an ethyl group, so two different groups. We list them in alphabetical order. The ethyl comes first, so we would call this ethyl methylamine. Example 9.9 says the nitrogen compound with three attached methyl groups is a gas with a strong fishy odor. Hey, what do you know? And is used as a smell agent in natural gas. Assign a common name to this amine. So you notice that we have one, two, three methyl groups. So it's going to be something methylamine. Well, if there's three of them, we would call it tri. So trimethyl amine, and that is the name, trimethylamine. And like I said, amines are not only are amines bases, but they also have that stinky fish odor. So our noses don't tend to like amines a whole lot. Now, again, I've gone over this already, a primary amine, secondary amine, and tertiary amine. Just this is the slide that's in the slide deck. So primary amine is when we have one R group attached to our nitrogen and two hydrogens. If we have a secondary amine, this is an amine having two R groups and one nitrogen, the nitrogen bound to at least, or one hydrogen, excuse me. And on the last one, a tertiary amine, you can see that in a tertiary amine, we have three alkyl groups. And so the nitrogen of a tertiary amine has no hydrogen bound to it. And so because of this, primary and secondary amines, they can do hydrogen bonding to themselves, in a sample, whereas a tertiary amine cannot do hydrogen bonding in a pure sample because even though it has a nitrogen, it's not bound directly to a hydrogen. All right, carvedilol is an amine used to treat high blood pressure and heart failure. It contains two amines. Classify each of the nitrogens of carvedilol as primary, secondary, or tertiary. Well, if we look at the one that's on the left-hand side, you can see that nitrogen is attached to two carbons. They're not drawn explicitly in the bond line structure, but we know they're there. And of course, there's one hydrogen. And so this would be a secondary amine, secondary amine. And in the other one that's in here, you can see the nitrogen has one hydrogen attached to it. It has two carbons attached to it, one here and one here. So this would also be a secondary amine. So both of these amines in this compound are secondary amines. Okay, now what about the properties of amines? And again, I want you to keep in mind that amines are what? They are weak bases. Okay, they are weak bases. Okay, they're not strong bases, they're weak bases. All right, so like I told you, amines typically behave as weak bases. They are the most common organic bases. And so here's a general reaction of if you put an amine, and this is a primary amine being shown here, if you put it in water, it's going to take a proton from water. So it's going to act as an H plus acceptor, and we end up with some kind of ammonium ion here, and we end up with hydroxide. Okay, so we end up with hydroxide, which is very basic. So here's a specific example. We take methylamine, put it in water. The methylamine takes on a proton from water. We get a methylammonium ion, and we're left over again with hydroxide. Now, that is an amine behaving as a base with water. But what if we were to react an amine with a strong acid like hydrochloric acid? Well, in that case, when you react an amine with a strong acid like hydrochloric acid, you actually end up with a salt. Okay, it's not table salt, it's an amine salt where we have a positive charge on our nitrogen and a negative charge on our chlorine. And they've given you a specific example here of methylamine plus HCl gives you methylammonium chloride. So again, the nitrogen took this hydrogen, so now instead of being NH2, it's now NH3, and then the chloride, Cl minus ion, is left over by itself. Okay, so let's see if we can finish this question. Phenylephrine is a medication used as a decongestant to dilate the pupil of the eye and to increase blood pressure. Complete the following reaction. So we have phenylephrine reacting with acetic acid. I have it labeled here. And so in acetic acid, there's only one acidic proton. It's this proton here, the one on the very end, the one attached to the oxygen. And then we have our nitrogen here, and our nitrogen is going to pick up the extra proton, the hydrogen atom. So we're going to redraw our aromatic ring. So there's our hydroxyl group. All right. Then we've got our CH and our OH here, another CH2 group. Then now our nitrogen is going to have an extra hydrogen. And so because of this extra hydrogen, it's going to have a positive charge. And then what's going to be left over is what the species after the acetic acid gives up that hydrogen ion. It's called the acetate ion. So I'll just write it here, CH3COO. And it has a negative charge. So this is our positive and negative charge. So the positive charge on the nitrogen and a negative charge on our acetate ion. So again, this is called an acetate ion. All right, for the next one, we have dimethylamine and water, in water. And I'll just draw a little line here so that we can see. Okay, so there we go. So in water, and what's going to happen is the dimethylamine is going to pick up an extra hydrogen from the water. So we're going to have CH3 NH, but now it's going to have the extra hydrogen and a positive charge. CH3, and we're going to be left over with a hydroxide ion like that. So remember, amines are weak bases. They pick up hydrogen ions, and then once they pick up a hydrogen ion, they adopt a positive charge. All right, amine salts. Amine salts may be named by changing the name of the amine to ammonium and adding the name of the negative ion derived from the acid. So whether it's chloride, bromide, iodide, etc. Amine salts have physical properties that are characteristic of other ionic compounds. They're white crystalline solids and have high melting points. So remember, ionic compounds, right? White crystalline solids, high melting points. Amine drugs are often given the form of salts so that they will dissolve in bodily fluids as they are more water soluble because they are ionic. And an example here is morphine, which is not soluble in water, but when they treat it with sulfuric acid, you end up with morphine sulfate, which is a water soluble compound. All right. So we again treat the amine with an acid to form a salt, and then the salt is going to be soluble in body fluids. Now, a quaternary ammonium salt, which we sometimes refer to as a quat, okay, or if you ever hear somebody talk about quats, they're talking about a quaternary ammonium salt, is an ionic compound containing a positively charged ion in which the four alkyl or aromatic groups are bonded to the nitrogen. And you can see that here in the choline ion and the acetylcholine ion. So what do they both have in common? They both have a nitrogen with 1, 2, 3, 4 groups attached. Here we have a nitrogen with 1, 2, 3, 4 groups attached, and we have the positive charge shown up here. Now, unlike other amine salts, quaternary ammonium salts contain no hydrogen attached to the nitrogen that can be removed by adding a base. And choline is an important quaternary ammonium ion that is a component of certain lipids. Acetylcholine is involved in the transmission of nerve impulses from one cell to another. Simple low molecular weights are gases at room temperature, but heavier, more complex compounds are solids and liquids. And so we can see here that methylamine, the one on the top, okay, it's a primary amine, it's very small, it has a boiling point of -6, it has a melting point of -94. Then we go to something like ethylamine, and what do you see? You notice that the melting point increases and the boiling point increases. But then we go back down to dimethylamine, and you can see that the boiling point is still low. But anyhow, you can see here that as the means get bigger and bigger, if we go all the way to something like triethylamine, that the boiling point is, almost to 90 degrees. So as they get bigger, generally speaking, the boiling points and melting points will increase. Now, like I told you, in order to have hydrogen bonding, you have to have a hydrogen bound to either oxygen or a hydrogen bound to nitrogen or a hydrogen bound to fluorine. Well, if we're talking about amines, if we have an amine that has a hydrogen bound to the nitrogen, it can participate in hydrogen bonding. Now, since nitrogen is less electronegative than oxygen, the hydrogen bonds aren't going to be as strong as they are when we have an oxygen hydrogen bond, and that's because the delta negative and delta plus charges aren't going to be as powerful, right? Because the difference in electronegativity between hydrogen and nitrogen isn't as great as hydrogen and oxygen's. Now, amines with fewer than 6 carbons are generally going to be soluble in water as a result of hydrogen bond formation with amine functional groups and the water molecules. But once we get more than 6 carbons, generally speaking, they're not going to be water soluble. And you can see here that a primary amine, you see a primary amine here is hydrogen bonding with water, and the hydrogen here is hydrogen bonding with the oxygen of water. You see something here with a secondary amine, but you notice with a tertiary amine, since there's no hydrogens attached to the nitrogen, the only hydrogen bond that could occur is between the nitrogen and the hydrogen of a water molecule.